And I want to take a minute to talk about something called continuity. And the definition of continuity, as it's written, may seem very straightforward, and it looks a lot simpler than what it really is. If a function is continuous, if f of x is continuous, all right, at a number they often call a. This is the case if the limit as x approaches a of f of x equals f of a. Again, seems like a pretty straightforward statement, all right? But you have to understand there's a lot that goes into this statement. There's a lot implied by this statement, right? So let's think about what all they're saying here. Okay, here's what they're saying. Let's start over here on the right-hand side. They're saying equals f of a, all right? That means, number one, f of a must exist, all right? So for a function to be continuous at a number, the function has to be defined at that number. Now, looking over at the left-hand side, they're saying that the limit as x approaches of a of f of x equals this. Well, that implies several different things. That implies limit as x approaches a from the left of f of x exists. The limit as x approaches a from the right of f of x exists. And it implies that the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. All right, so this is, there's several different things that come out of this one statement. The function has to exist at that value. The left-hand limit has to exist. The right-hand limit has to exist. And therefore, the overall limit exists because the left equals the right. And then you can conclude, if all of those things are true, then you can conclude continuity at a single point. Now, the definitions, there are definitions here of continuous from the right, continuous from the left. And for those definitions, you would just use, for example, if they're saying a function is continuous from the right, then the left-hand limit part of this statement doesn't come into the picture. You just remove the left-hand part, and continuous from the right simply says that the function has to exist at that value, and the right-hand limit has to equal the function value, and you've got continuous from the right. And continuous from the left, similarly, the function value must exist, and the left-hand limit has to exist and has to equal that function value. Now, they ask you to show continuity on a particular interval. Now, if you tried to use this definition exactly as written to show continuity on an interval, you'd be at it for the rest of your life, okay? Because you'd have to show continuity at every single number in that interval. And as we all know, there are infinitely many values in any interval, so you can't do it that way. So what you have to do is use the limit laws. You must reach this statement. You must get to the point where you can say limit as x approaches a of f of x equals f of a, and you must do it using the limit laws instead of doing it one numerical value at a time, finding one limit at a time. All right, so for example, if you had an f of x equaling something like 1 minus the square root 1 minus x squared, you would start off by saying that the limit as x approaches a, so again, notice I'm not putting in a specific value, I'm just putting in a arbitrary a value of f of x, would be equal to the limit as x approaches a of 1 minus the square root of 1 minus x squared. And then you start using the limit laws, like for example, the law that says the difference of limits is the limit of differences, so this becomes limit as x approaches a of 1 minus the limit as x approaches a of square root of 1 minus x squared. And then you have the law that says the limit of a constant is just that constant, so this becomes a 1. All right, minus, and then there's a law that says that with powers, and square root is a 1/2 power, that the limit can come in thusly. And then once again, you can use difference of limits as limit of differences. Once again, you can use the fact that the limit of a constant is just that constant. You can now, they specifically stated a limit law for x squared. All right, and it just so happens that's the same thing as f of a. And it just so happens that turns out to be f of a. So here, in a very long and drawn out fashion, all right, we've shown that the limit is the same as the function value. So we've proved continuity, all right? And we've actually proved continuity anywhere where the function is defined. And it is defined, all right? They originally said, show that it's continuous on the interval -1 to 1, and all that's in the domain, okay? So that's all in the domain, so we've got continuity of the function on its entire domain. It's continuous anywhere and everywhere it exists, all right? We also learn that if you have f and g that are continuous, then f plus g is continuous, f minus g is continuous, a constant times a function is continuous, the product of the functions is continuous, and the quotient of the functions will be continuous as long as the one on the bottom never equals 0. And what this establishes for us is the first of what I just personally call red flags. When you're computing a limit and a 0 appears in the bottom, that's a red flag. Something has just happened that you need to be on the lookout for. Something you need to be watching out for very carefully has just occurred. All right. So therefore, what that brings us to is several entire families of functions that are continuous. For example, polynomials, rationals, roots, trigonometric, inverse trigonometric, exponential, and logarithmics are continuous as long as you stay within their domain. Of course, you're not allowed to venture outside the domain of the function, but they are continuous on their entire domain. All right, so what that allows us to do then is to evaluate limits and understand the continuity of literally tens of thousands of functions. And now that we're aware of that, so let's look at a couple of problems as they appear in the book. Let me just jump to the book real quick. All right, at least the book that I'm reading out of today, and let's look at a few problems. I have some graphics in here that I wanted to look at. All right, so let's do that. Here, let me drop it down to one page so it's a little bit larger, easier to see. All right, here we have a couple graphics I wanted to look at. Like, for example, problem number 3. From the graph of f, state the numbers at which f is discontinuous, and let's explain why. All right, left to right, where do we have discontinuities? At -4, we have a discontinuity. Right here, -4, we have a discontinuity. Why? Well, the left-hand limit exists. The right-hand limit exists. They're equal, so therefore the overall limit exists, but the function doesn't exist. Okay? Compare that to at -2. What's going on? Well, at -2, the left-hand limit exists. The right-hand limit exists. The function value exists, but the left-hand limit and the right-hand limit are not equal. Therefore, the overall limit doesn't exist. So it's a discontinuity. -2 is a positive 2 is a discontinuity for the same reason. 4, you have a right-hand limit, but on the left-hand side, you're going to -infinity. Therefore, you don't have continuity. right? So anywhere you've got these breaks, gaps, and jumps in the graph, there you'll have discontinuity. Like up here on problem number 4, what's going on at -2? Left-hand limit exists, right-hand limit exists, function value exists, but the left-hand limit doesn't equal the right-hand limit, and neither one of them equal the function value. So therefore, you have discontinuity. We have some others here that I specifically wanted to address. Jumping to, I want to skip over to number 37. No, I'm sorry, 15. Back it up. Number 15. Explain why the function is discontinuous at a given number a. So, for number 15, why would it be discontinuous when a is equal to 1? Now, putting an a 1 in for x gives you division by 0. All right? So, 0 in the bottom of a fraction is going to give you your discontinuity. Now, in number 16, they want to know why is it discontinuous at 1. Well, plugging a 1 in the bottom of this fraction would give you a 0, but they're specifically telling you you don't use this version of the definition for 1. At 1, the function value is equal to simply a 2. So what's going on? What's going on? Well, for that one, the graph would be helpful. So if you had a graph of 1 over x minus 1, get that ready here. That's what it looks like. All right, so what's happening is you're on that graph, as you come in from the left, you're heading towards negative infinity. As you come in from the right, you're heading towards positive infinity. So for that particular function, the left-hand limit doesn't exist because it's negative infinity, and the right-hand limit doesn't exist. Either one of those by themselves is enough for discontinuity at 1. Generally speaking, a vertical asymptote is a discontinuity. All right, now if you skip on down to number 18, that one's a little bit more subtle. Let's take a look at number 18. If you had, with number 18, if you had f of x equaling x squared minus x on top and x squared minus 1 on the bottom, and you want to know what's going on at 1. Well, they specifically tell you on number 18, don't plug in a 1, right? Because you will get 0 in the bottom of the fraction. So let's look on paper what happens at 1. All right, with this, I'll factor out an x, leaves me an x minus x and x minus 1 on top. Factor this one to get x minus 1, x plus 1. X minus 1's cancel, and I get an x over an x plus 1. All right, now in this particular function, if you were to plug in the 1, you'd get a half. So what this function is doing is, as it comes in from the left and as it comes in from the right, it's approaching 1/2. All right, so this function actually has a left-hand limit, it has a right-hand limit, and they're equal to each other. So the limit of this f of x as x approaches 1 does equal a half. So this thing has a left hand, it has a right hand, they're equal. It has an overall limit, it's a half. So why do we have a discontinuity? Because they've defined the function to specifically equal 1 when the x value is 1. So 18 has discontinuity that could be, shall we say, fixed or repaired. And it could be repaired simply by making this 1 a 1/2. By making the function value equal the limits, you would create continuity where there was discontinuity. So if you look at the problems that I almost did first, problems like 37, 38, 39, what you're going to have to look at, if you look at the 1 plus x squared, the 2 minus x, the x minus 2 squared, all of those functions by themselves are continuous. It's just the problem is, do they come in from the left and meet up in the same place when they came in from the right? Okay, For example, number 37, if you plug in a 0, you get a 1. Right here in this first part of the definition. You plug in a 0 here and you get a 2. So this function's coming in from the left side of 0, approaching a 1. Coming in from the right side of 0, approaching a 2. So you've got a discontinuity at 0. Plug a 2 in here, you get a 0. Plug a 2 in here, you get a 0. So as it comes in at 2 from the left, and as it comes in from 2 from the right, it's continuous because it's doing the same thing on both sides. So the discontinuity here would be at the 0 value. Okay, and backing up to number 35, why is this function continuous on all real numbers? Well, x squared is always continuous. Square root of x is always continuous on its domain. All right, and this graph doesn't start until 1, so we have continuity. And also at 1, x squared is 1, and square root of x is 1. So as you approach 1, it's doing the same thing on both sides. Why is 36 continuous on all real numbers? Sine is continuous, cosine is continuous, and as you come in to the left of pi over 4, and as you come in from the right of pi over 4, the sine of pi over 4 is square root of 2 over 2. The cosine of pi over 4 is square root of 2 over 2. So as you come in from the left, as you come in from the right, the function is doing the same thing on both sides, so you have continuity. All right? So those are the things to look for. Does the left-hand limit exist? Does the right-hand limit exist? Does the overall limit exist? And does it equal the function value? And that's how you know whether or not you have continuity. All right? And looking at problems like number 21, you just have to make sure, again, the same stipulations are met. And again, with these problems, just make sure your limits exist, left hand, right hand, overall, and make sure they equal the function value, and you will have your continuity.